Hello and welcome back to Broadcast from the Bunker. First off, I want to make sure everybody's got their student ID on them. Very important while we're at home here. Second, today's hot topic, how do we describe the process of chemical weathering? We're going to start out with our do now questions, 25 to 28, so jump in your GC and give them some love. Okay, starting out on 25 here, some constellations appear observed in the summer skies in New York State are different from those observed in the winter skies. The best explanation for this? Well, remember, if it's talking about different seasons, you got to be talking about a revolution type thing. And with the stars, it's pretty interesting. So let's just say this is let's say this is the sun. Obviously, it's a model here. Let's say it's the sun. But if I'm looking this way, the sun is so bright, I can't see behind there. So everything behind this sun, I can't see, right? But if I turned around and looked the other way, it's dark that way, I'd be able to see that. And that's what goes on. So as the Earth goes around the sun, it's able to see different parts of the sky, and that's why you'll see different constellations throughout the year, okay? So what's going on here? Why do we see different constellations? Well, the Earth is revolving around the sun. And if you remember, we had a lab on that in the classroom where we had this bright light in the middle, and you guys had to revolve around it and then rotate to see which constellations you could see. Okay. 26 through 28 refer to these four diagrams here. So 26 is asking the sun's apparent path through the sky on this day as a result of, well, the sun's path through the sky any day, right? The reason the sun rises and sets is because of the Earth's rotation. So you don't even need the top diagram for that, but got to be talking about a rotation. So Earth's rotation, D right there. All right, 27. It says, what time of day is shown by the sun's present position at location A? So let's go to location A. All right, we'll zoom in on that. Okay, now take a look. Now here's north, here's south. So if you remember your compass, right, west has got to be over here, which puts east over here. I'm just going to label that right away. All right, again, pardon my handwriting. I'm writing on a vertical screen there. But anyway, so we're going to rise in the east, and let's say we rise around, let's call it 6 a.m. It looks like it's an equinox day, and you usually rise around 6 a.m. So 15 degrees an hour would be 6, 7, 8, 9, 10, 11, 12, noon, solar noon, 1, 2, 3 or so p.m. So that'd be about 3 p.m. Based on that 15 degree per hour sun path in the arc. So we said 3 p.m., so we got to go with afternoon here. And just write in there approximately 3 p.m. All right, 28. Did I skip one? No, that's it. 28. To an observer at location A, the sun will appear to move from, well, remember, it doesn't matter where you are on Earth, the sun's going to rise in the east, set in the west, generally speaking. So it's going to be east to west, and that rate of 15 degrees per hour is because the Earth's rotation is 15 degrees per hour. Okay? The only strange exception to this one here would be location D. Oh, no, never mind that. Okay. So we're going with east to west, 15 degrees per hour. All right, if you have any questions on those, please leave them down in the comment section, or again, you can shoot me a remind. Let's jump back to the GC for the lesson. Okay, tonight's homework, make sure you got your textbook going, pages 239 to 249. I'm looking for 15 bullets, and those please email me. And again, folks, thank you for your continued persistence and patience with the internet issues, making it challenging to complete those assignments, but keep at it. As far as the Castle Learning, they just sent us an email. They seem to have less traffic after 4 p.m., so for Castle assignments, try after 4. Okay? All right. So chemical weathering, if you look in the pictures here, you got a piece of rusty metal there, and that happens because the oxygen in the air oxidizes iron, right, in steel. Over here you have what looks like a cave, right? Limestone is a sedimentary rock that dissolves in acid. So when you get acid rain, you get these dissolving of caves, and those are two of the things we'll be talking about in today's lesson. Okay. This is the story of Cleopatra's obelisk, commonly called Cleopatras Needle. It was brought over from Egypt in the 1800s, and it came down the Nile and across the Atlantic, and they put it up in Central Park. You can actually go see it. It's up by the Museum of Natural History. Anyway, it had these gorgeous hieroglyphics on it, and it told the story of Cleopatra's life and some other things. But in New York, we have a much more humid climate than Egypt, and we get a lot of acid rain that Egypt doesn't get. So in the deserts of Egypt, it lasted for thousands of years almost perfectly. But then when we brought it over to New York, well, you tell me, very difficult to read those hieroglyphics now because the acid rain dissolved it. And this is made out of limestone, which has calcite in it, and of course that reacts to acids. So kind of a reality check there. You got to be careful with moving monuments around or they will be destroyed. Okay, that is classic chemical weathering. Okay, there's a plaque at the base. If you do go into the city to check it out, it tells you a little about the story of Cleopatra and the story of the obelisk. Okay, here's a little experiment if you could set it up at your house. Very simple to do. Get 2 glasses, one with water, put vinegar in the other one, and then just take a piece of chalk and break it in half and put it in each one. Carve your initials on it. This way you could see what's going to happen and put them in there. And of course, wait a few minutes and a little something will happen. Wonder if you could think of an inference. What do you think will happen at this point? We'll come back to that at the end of the lesson. Okay? All right, here's a little background reading. Make sure you read that through. Tells you about chemical weathering. Here's your definition: chemical reaction that breaks down the minerals in the rock. It turns into a new substance. This is not like physical weathering where things just get smaller. You're actually changing the chemical composition. 2 gravestones here, one much less weathered than the other. Well, different rocks have different minerals in them, if you recall, and they'll be more or less resistant to chemical weathering. Okay? Everybody's left their bicycle outside in the rain. You come out the next day, your chain's all rusty. Again, that's because of that iron oxidizing with the oxygen in our atmosphere. Okay? Oxidation is a form of chemical weathering. It occurs when oxygen in the atmosphere combines with certain minerals in the rock and gives you a red rust color. And you can sand it down and get clear metal again, but you lost a little bit of metal. You're actually losing some material there. Like, for example, your bike chain, if it keeps getting rusty, it's getting thinner and thinner and thinner, and it's going to snap on you. So make sure you keep it oiled and keep it covered if you can so that it lasts much longer. You can see the red in the rocks here. Again, that's from iron in the rocks. All right? Beautiful layering, sedimentary, and of course the red iron again. Underground, caves are made out of limestone, like we said, and limestone dissolves with acid, right? It's made from calcite. That is a form of chemical weathering. They call that carbonation, where carbonic acid reacts with rocks and minerals such as calcite, limestone, and marble. All right? Everybody breathe in. Breathe out. You just are responsible for creating acid rain. That's right. You exhale carbon dioxide, and that will combine in the atmosphere to make a weak acid, right? Carbonic acid is a weak one, but still enough to gradually break down limestone over time. Okay, so you'll make caves below ground, you'll make sinkholes above the ground. Imagine that right there, right? That was all limestone down below that dissolved from acid rain, and then of course the street collapsed. A lot of other neat pictures there. That's just a higher angle of that one. Here's one that collapsed a long time ago, and since then trees started growing in the bottom of that sinkhole. Here's, what you don't want to happen to you when you go shopping, right? The parking lot collapsed from a sinkhole underneath. There's a monster one. All from this carbonation, this dissolving of limestone because of acid rain. Closer to home, I don't know if there's any Corvette fans out there. There's a Corvette Museum that was built on top of limestone. And over time, again, the ground underneath it dissolved. Well, quick little clip of what happened. Check it out. So these are all the Corvettes before the catastrophe. Beautiful cars. And then all of a sudden, one night, they'll show you a little security video. Carbonation occurred and the ground collapsed and you could see the cars just start to fall into the earth. A total of 8 Corvettes went into the hole that day. Obviously, if you're a Corvette lover, that's a real heartbreaker. Watch closely in the middle. There's the floor collapsing. You'll see like a little bit of dust and stuff starting to come up. And then a few seconds later, the rest of the floor gives way as that limestone underneath completely dissolved over time. And wait for it, wait for it. There they go. Down into the earth. Again, 8 total cars went down. They did, of course, do recovery efforts to try to pull some out. There you can see that was the first one. That was the last one to fall in. It was the least damaged. But the rest of these are in pretty rough shape. That one was even able to be driven out. But the rest of them were not as lucky, that's for sure. You can see the hole, and they're trying to salvage what they can. That's a classic 60s Corvette coming at you right there. Anyway, check it out. Just type in a Corvette Museum sinkhole and it'll pop up for you. Okay, let's keep rolling here. No pun intended, right? Car rolling. I tell you. Here's the Statue of Liberty. Now, the Statue of Liberty used to be nice and tan, but you know, it likes to turn green. Well, it too is succumbing to chemical weathering. But not from iron this time. There's a lot of copper in the Statue of Liberty, and copper turns green when it oxidizes. So when you see it, that's what you're used to seeing. But, you know, originally it was this color. Back when I was a kid, they sold coins, the Statue of Liberty coins, to try to raise money to bring the statue back to its original state. And they did. They set up a scaffolding. They ground off all the oxidized copper, and it looked like that once again. But in no time at all, it went back to green because it's just a constant process, this chemical weathering. You're not going to stop it. You could slow it down, but you're not going to stop it. All right? Acid rain, a major contributor to chemical weathering. Gases in the atmosphere react with water, oxygen, and other chemicals to form various acidic compounds. All right? Make sure you're getting these in your notes, folks. Hydration, another form of chemical weathering. You take a solid mineral. This looks like a potassium feldspar. And just from regular rain over time, that water will soak in and break it down into a very, very fine substance that we know well, right? We call it clay. And there it is, all broken down. So potassium feldspar is in granite. It's the pink stuff. And over time, it will succumb to chemical weathering, the potassium feldspar. The quartz, not so much, but the potassium feldspar will. It's called hydration. Water combines with different minerals and turns hard minerals into a soft substrate. All right? And there's your clay. What type of climate do you think chemical weathering is most likely to occur? Well, if we need a lot of rain, it's got to be a humid climate. And chemical reactions also seem to like heat. So warm, moist climates. Well, if that's not warm and moist, I don't know what is. The best climate for chemical weathering are the tropics, right? Warm, moist. You get higher temperatures, lots of moisture. When an animal dies in the forest in the tropics, it breaks down very quickly. But if an animal dies up by the poles, it'll be preserved for thousands of years, like the mammoths up there, because it's very dry and it's very cold. Okay? So here's your experiment. I hope you did set it up. Do you have your results that look something like that? Completely weathered down? Yeah, to show you what it looks like in real life, as soon as you drop the chalk in, you should have seen something like this. And there it goes. That chalk will dissolve very quickly. That's simply vinegar, folks. That's not some kind of crazy acid. That's just vinegar, which is acidic. Chalk is made, is a type of limestone. It's a calcium carbonate, so it breaks down. Okay, and there it is, chemical weathering. Quick summary question, describe the difference between the two chalks. Well, hopefully you look carefully at them. One is completely broken down into like a sludge. The other you could still recognize. The type of chemical weathering that occurred on the chalk, well, your carbonation there, right? It totally broke down. How is this process of the chalk similar to Cleopatra's Needle? Well, Cleopatra's Needle was made out of limestone, which has calcite in it, just like the chalk, and it gets dissolved with acid. Okay. A couple of summary regions questions. In which type of climate does chemical weathering usually occur most rapidly? Well, remember, that's like the tropics. It's going to be warmer and more moist. All right. Second one there, which change in the climate of New York State would most likely cause the greatest increase in chemical weathering? How could you speed up chemical weathering? Well, you'd have to add more moisture and increase the temperature. So which change in climate here? Well, more precipitation is a good one. Certainly not lower temperatures. Higher pressure would mean drier. That's no good. Lower humidity means less moisture. So yeah, you'd have to go with more rain in the summer, and that would speed up your chemical reactions. Okay? All right, I hope you followed that. Hope it makes sense to you. Any questions? Remember, please simply type them in the YouTube section below, or remind me at that code there if you have not joined the Remind yet. All right, folks? Take care.